JRE 2416. Scientists say countless versions of you may exist right now in parallel worlds.
You've done an amazing job in this book of trying to boil it down for dummies like me, but it's hard. It is a complicated and insanely nuanced subject.
Yeah.
And it's one of those things where it like this many worlds theory, for one example, the just the possibility that there's like, explain that.
Sure.
Explain for people that don't understand what quantum mechanics even means. Give them just like a little bit of that, and then explain many worlds theory.
Yeah, good. This is what I'm here to do. So,
thank you.
You know, an electron, take an electron. Quantum mechanics should apply to the entire universe, but it becomes unmistakable when you look at little tiny things, right? So we always are talking about electrons or atoms and so forth. An electron has a position and, well, sorry, let me not even say that. Even that was wrong. It's just so hard to correctly talk about quantum mechanics, right? If you were Isaac Newton, before there was quantum mechanics, there was classical mechanics. And basically, quantum mechanics and classical mechanics are the only two big frameworks that have ever existed in physics. You know, classical mechanics was so good that everyone thought that was just right, and it was all a matter of filling the details until quantum mechanics came along and changed things. In classical mechanics, an electron is a point. It has a position, a location in space, and it has a velocity. It's moving somewhere. And from that, you can predict what's going to happen, okay? Quantum mechanics says, no. The electron has a wave function. So there's a wave. You know, sometimes you hear this debate about are things like electrons and photons particles or waves. The answer is that they are waves. And the wave function has this weird property that when you're not looking at it, it's a wave, it's all spread out or it's localized somewhere, but it obeys an equation, the Schrodinger equation. So far, so good, just like regular physics. There's a thing, the wave function, it obeys an equation, the Schrodinger equation. You can predict what's going to happen next. But the weird thing about quantum mechanics is that there's a whole separate set of rules for what happens when you look at the thing, when you observe it, when you measure it.
That's where things get squirrely with people describing it, right?
Yes.
And that's where they want to go woo-woo on you.
It's an opening to be woo-woo, right? When you say, like, what do you mean observe something? Like, does it have to be a conscious being? Can it be a video camera? You know, that's just weird, right?
Is it the act of measuring that changes things?
Well, this is the puzzle, okay? This is what is called the measurement problem of quantum mechanics, that the rules we teach our students at Caltech or anywhere else when we teach them quantum mechanics in their sophomore year of college, the rules say when a system is observed, when it is measured, its state, its wave function changes dramatically, suddenly, and unpredictably.
Now, let me ask you this. How do we know this based on if you're measuring it and it changes? How do we know? Because we didn't measure it before. Like, what observations are we making that we understand the state of it before it's measured without measuring it?
Good. There's a couple of ways. So let me make things even simpler. Forget about where the electron is located and think about the electron is spinning. Right? Okay. The electron is spinning just like the Earth spins. It's really exactly like that. It's like a little spinning top, except when you measure the spin, you can sort of send the electron through a magnetic field and it will get deflected either up or down, depending on whether it's spin up or spin down. You only ever get one of two answers. It's either going up or going down. It's nowhere in between. This is an empirical measured fact, okay? So that's a part of quantum mechanics. That's the quantum fact, that there's discrete set of possible answers to this question. Is it spinning clockwise or counterclockwise? Yes or no. It's just those two possibilities, nowhere in between. So if you have a magnetic field that is oriented vertically, send your electron through it, it gets deflected up, you say, oh, it's spin up. So now I've measured its spin. Now I know what its state is. If I send it through another magnetic field or oriented vertically, it will always be deflected up every single time. We know what it is. We're going to measure it. Measuring it in this case doesn't change it. It's in exactly that state. We know it, okay? Now let's send it through a magnetic field that is oriented horizontally. So it's going to be deflected either right or left. We know exactly what state it's in. It's spinning this way. But when you send it through that magnetic field that's oriented horizontally, it gets deflected left or right 50-50, unpredictably. There's no way we can predict it. And then once it is, so okay, now it's been spinning up, you measured its spin left, let's say, send it through another magnet that is going vertically. And now it's 50-50 again. It could be spin up or spin down. So somehow, even though we knew exactly what state it was in, we couldn't predict what would happen next. That is part of quantum mechanics.
So the act of sending it through these things where it makes it vertical or horizontal, what is happening to it when it's going through these things?
So in quantum mechanics, what we say is that it's not that we don't know whether the electron is spinning clockwise or counterclockwise. It can be in a superposition of both. That's just the spin version of the position of the electron can be spread out in a wave, right? It's truly not just that we are lacking some knowledge. It's that the knowledge really isn't there. And again, this is how we teach quantum mechanics in textbooks. And then I'm going to correct it because Many Worlds is much better. But This is the standard textbook version. There's a wave function. The wave function for a spin is it's either up or down or some combination. And then there's a rule that says when you measure the spin, you only get up or down. You don't see the wave function. Just like the cloud that you have for the electron's position, when you look at it, you see it at a location. So another way to make the same argument is take a little piece of, I have a nice little image of this when I give talks, a little piece of uranium. So it's a radioactive little chunk of metal, and you put it in a bubble chamber. So it is emitting radioactive particles, and you detect the particles. You can see a little streak of motion when the particle leaves the uranium, okay? Well, like I said, when you're not looking at it, this electron is supposed to obey an equation, the Schrödinger equation. And you can ask what the prediction is when a radioactive nucleus decays and gives off an electron. What is its wave function going to do? What is the wave function of the electron going to be? And the answer is it goes off in a spherical wave. It goes off in all directions at once.
Evenly.
Yeah. All directions evenly. But you never see that.
Is that roughly based on
line.
the shape of the piece of uranium? Does it vary?
No, because the electron gets from one individual nucleus of an atom, right? So what the uranium is doing doesn't matter. It's just that one atom matters. And the easiest thing for the electron to do is just to go out in a sphere. It doesn't have to. It can go out in higher energy states. But the point is, it's not going out in a straight line. But when you look at it, you see a straight line, right? That's the fundamental mystery of quantum mechanics, that how we describe the thing when we're not looking at it is different than what we see when we look at it. So
when you're in pursuit of an understanding, a deeper understanding of quantum mechanics, when you're thinking about people from the 1900s that are just sort of basically getting the first steps going to understand this stuff, when you're talking about this lack of funding and the lack of encouragement for people to pursue quantum mechanics, you strongly feel like there are answers to these questions.
Yeah, that's right.
That we just need better tools and a better understanding, better equations, more time.
Yeah, me and Einstein think this, right? So Einstein is one of the secret heroes of the book because he has this reputation as someone who just couldn't quite accept quantum mechanics. The title, Something Deeply Hidden, is a quote from Einstein when he was talking about when he was a kid and he had a compass, right? And he was given his first magnetic compass and he could rotate it this way and that way and it always pointed north. And you and I would go, that's cool. But he was Einstein. He's like, wow, this is amazing. Why? How does it know where north is, right? And he said there must be something deeply hidden that explains why it's doing this mysterious thing. And he felt the same way about quantum mechanics, that we gave these set of rules, which are called the Copenhagen interpretation of quantum mechanics. One set of rules for when you're looking at it, one set of rules for when you're not. And Einstein was like, oh, come on. Clearly, this is not the final answer to the nature of reality, right? He wanted to know God's thoughts. He's like, I want to know everything. We're not done yet. There must be more going on. And so Many Worlds is one of the proposed answers to what could be going on. It's not the only one. There's alternatives, but it's definitely my favorite. It's definitely the easiest one to write down. Let's put it that way.
Okay, so hit us with this many worlds theory.
Okay, so think about this electron. You say that it could be either spin up or spin down. It's a combination of both. That's its wave function. You measure it, you only ever see spin up or spin down. So Copenhagen says that's because the wave function suddenly changed, snapped into place when you observed it. Don't ask me what it means to observe something. That's not what Copenhagen lets you ask.
Okay.
Many Worlds says what you're missing is two things. Number one, you're a quantum system. You're obeying the rules of quantum mechanics. You're made of atoms and electrons and so forth. You have a wave function too, okay? So you're secretly treating yourself as a classical thing when you make that measurement, but you really should be treating yourself quantum mechanically, right? That's one thing. And the other thing is something that Einstein invented, namely called entanglement. When quantum mechanics says there's a wave function for a system, it doesn't say there's a separate wave function for every particle, right? It says that there's only one wave function for the whole universe. So the way I like to say it is, imagine two particles come in and bounce off of each other. Either one has a wave function and it's unpredictable exactly what angle it's going to go off at. So both of the particles that go off, you don't know where they're going. But because momentum is conserved, if they came in at equal velocities, they'll go out at equal velocities and in opposite directions. If you measure one, then you know where the other one is going, right? That's entanglement. The observed state of one system can be related to the observed state of another system. So those are the two ingredients. You're a quantum system, and quantum systems can be entangled with each other. So Hugh Everett, who was a graduate student when he invented this idea in the 1950s, said, look, when you measure that electron, what happens physically? Like, forget about you're a person, you're conscious, all of that BS. Like, you're a physical system, you obey the Schrodinger equation. You are a quantum mechanical system, you obey the laws of physics. So you look at the electron, your wave function changes. It used to be you're just a person doing whatever you do, but then after you look at the electron, you become entangled with it. And it splits. So there is one part of the wave function that says the electron was spinning clockwise and you measured it spinning clockwise. And there's another part of the wave function that says the electron was spinning counterclockwise and you saw it spinning counterclockwise. Now, everybody knows this. Like that far, it's not controversial at all. That's clearly the prediction of the equations of quantum mechanics. But everyone else said, well, that means that I'm some weird combination of I saw it spinning one way and I saw it spinning the other way, but I've never felt that way. When I look at real electrons, I see them one way or the other. That can't be right. That can't be the final answer. The wave function must somehow collapse. And Everett said, no, what you're missing is there's now two separate worlds. Both of those part of the wave function are real, but they're different worlds. They will never interact with each other again. What happens in one part of the wave function will not affect what happens in the other part. So now there's a version of you that saw the electron spinning clockwise, and there's another version of you that saw it spinning counterclockwise. And that's just taking seriously the prediction of quantum mechanics. It's not adding any extra stuff, any extra worlds, anything like that.
That is the part where my brain broke.
All right.
The idea that there's a you that observes it going clockwise and a you that observes it going in a different direction, like that is so hard to understand. Do you apply this in your regular life? Like, do you think, like when you go home and you say hi to your wife and you open up the refrigerator, do you think of yourself as this quantum being that's existing in this super state?
So, I mean, there's a couple of answers to that. One is, sure, if I think about it, like I really do believe it. I have a chapter in the book, which my editor resisted at first, but then he let me get away with it, which is a dialogue between a young philosopher and her father, who is a physicist. And the father is skeptical about all this philosophical nonsense, and she tries to explain how many worlds works to him. And at the end, his last question is, do you really believe this? Are you really taking this seriously? And look, that's a perfectly good question. It's a very respectable question because it is many worlds. It's not crazy or weird or bizarre, but it's certainly very, very far away from our everyday experience, right? So what it's asking you to do is to say, I have these equations. They are really, really good at fitting what I do observe in the world and making predictions. I can build the Large Hadron Collider, et cetera. I will take them seriously even for things that I can't directly observe, because they're the best equations I have, right? Until a better set of equations come along, I will believe these equations. And the implication of that is, there's a whole bunch of worlds, like a huge number, like a real, humongously, unimaginably big number, maybe an infinite number, maybe finite, we don't know, of different copies of you, and they're being created all the time. The good news is that it doesn't really affect how you go through your life. It doesn't really imply that you should behave any differently than you would if you just lived in one world.
But do you think of each choice that you make possibly changing everything about the world that you exist in? How are you looking at it? You know what I'm saying? Because you are a guy who probably understands it as good as anybody that's alive. So as weird as this stuff sounds, to me it sounds like it's almost impossible for me to comprehend. So I'm trying to filter it through your understanding of it.
Well, I think that...
He's taking his jacket off. We're getting serious.
I know. It's getting hot in here. Physics is heating us up. Yeah, I'm not exactly sure how to say it the best. It doesn't change who you are. It's certainly not true that you making a decision is what branches the wave function of the universe. I guess that's the right thing to say.
Good, because I want to stop all woo.
Yeah, you can't do
before
that.
It happens.
Everyone, believe me,
brakes.
The joke about how certain political choices imply that we're living in the wrong branch of the wave function has been made many, many times, right? But
okay.
It's not that your choices create different universes. Different universes get created, and maybe you're different in them by a little bit. In fact, I like to point out there is an app you can download if you have an iPhone called Universe Splitter, which will branch the wave function of the universe for you. And then if you agree ahead of time to do one thing in one branch and another thing in another branch, then there will be multiple copies of you who are living different lives. And then you can deal with that and your therapist however you like. But
what is the application exactly doing?
What it's doing is basically a version of measuring the spin of
It's called Universe Splitter?
Universe Splitter. It's only for iPhones.
I'm going to grab this right now.
But,
sorry, Android people.
Yeah, sorry. It's not even a web page. It's only an app. There's equivalent web pages. But.
Okay, I'm pulling it up right now.
Yeah, and what you can do, basically it sends a signal to a lab that coincidentally is located in Geneva, Switzerland, but has nothing to do with the Higgs boson or anything like that. They send a single photon down a pipe to what's called a beam splitter. So the wave function of the photon goes 50-50. It gets sent left. It gets sent right. And if you agree, and so then it sends back whether you ended up in the branch of the wave function where it went left or where it went. There you go. 199. Come on.
Yeah.
The power of changing the universe is in your hands.
I downloaded it.
Good.
I got it. I paid for it. I got it right here.
Yeah.
All right.
So if you have any tough choices, you can type in I want to have pizza or I want to have Chinese food for dinner tonight.
Well, it says in one universe I will take a chance. In the other one I will play it safe.
Yeah, but you can correct those. You can fill in whatever you want.
Really?
Yeah, that's the good part.
But what is happening with this
I will
app?
ask her to marry me. I will not ask her to marry me.
Is
right?
this
I will accept this job. I will go somewhere else.
Equivalent of a quantum fortune cookie?
Yeah. But
Yes.
except that all possible fortunes are obtained in different universes. The bad news is you can't ever find out how things went in the other universe. You can't talk to the different universes.
That's the problem, right?
Yeah, that's
so
the problem,
people will be
right.
paralyzed by analysis.
That's why you should act the same as if you just lived in one universe, because you can never talk to the people in the other ones.
So, but now let's hit the brakes on the woo again.
Yeah.
Because people would like to believe that there are there an infinite number of yous existing at the exact same time, making various choices which send you off in different directions?
So, number one, we don't know if it's infinite number or just really big, but there's certainly a really, really big number. It's big enough to be, big enough for whatever you want. But it's not everything. The theory does not say everything happens somewhere, right? The theory says the Schrödinger equation is obeyed. There's an equation that is obeyed. So electrons will never convert into protons because electrons are negatively charged and protons are positively charged. And nowhere in the Schrödinger equation can you violate the conservation of charge, right? So there's plenty of things that don't happen, but then there are plenty of things that do happen. And some things are more likely than others for you to experience. So again, it's sort of it's a mind-bendy thing, but it's a straightforward prediction of the equations, and it doesn't affect our lives. There's no rule that says, to be a moral person, to be a good utilitarian and make the world happy, knowing that the wave function is branching into multiple copies, I should act differently somehow. It's exactly the same as it would be in the ordinary world.
So, and you are the ordinary world, no matter how many copies of you there are, or how many versions of you there are.
There's nothing. So when all these copies are being made, there's no essence of you that is traveling through one of the copies, right?
Right.
All of these people are separate people. So I use the analogy, it's like identical twins. They were the same zygote or whatever, and now they're different people, okay? So that's the same thing. Like you're you now, and if you hit the button and branch the wave function, there'll be two different people, both of whom used to be you, but they're not the same person anymore because different things happen to them.
Now, when people think about the concept of quantum mechanics, and the way you're talking about describing things in the micro and the macro, you think of your existence itself in a very similar manner, the way you think of electrons, the way you think of things being quantum, is that you are a combination of all these quantum things.
Yeah.
So you don't operate in some sort of static state that's very like here and now and carbon, and you can put it on a scale and it'll never change. There's constant versions of you.
Yeah, it's kind of like a whooshing where, more and more versions of you are being created all the time. And it's an interesting thing because even the best trained physicists sort of think intuitively classically. Like, look, here's a table, there's a bottle, right?
You have
and,
to.
You have
Red
to.
light comes, hit the brakes.
And this is how we evolved, right?
Yes.
This is how our brains work, right? And like I said, many worlds is one respectable version of quantum mechanics. There are other respectable versions, more respectable than the textbook presentation. But they all the other ones somehow lean on our classical experience. And the textbook version certainly does. It says, like, you're a classical person observing a quantum mechanical system and so forth. And Everett, when he was a graduate student, he had arguments across the ocean with people in Copenhagen, who tried to push their way forward. And he's like, why do you get to be classical and the electron has to be quantum? Like, why aren't you quantum? Like, why isn't everything, what's so special about you, really?
Right.
And he was trying to think of the quantum mechanics of the whole universe, right? Where there's not a separate observer outside because he's doing the whole universe all at once. And so everything had to be quantum. And I think that that's another thing that is pushing us to appreciate the foundations of quantum mechanics a little bit more, is that we're trying to understand quantum gravity. We're trying to understand quantum cosmology, the universe all at once, obeying the rules of quantum mechanics. And the conventional Copenhagen theory is just not up to it.